many, 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 many other directions. Sure, and there's many practical uses for knowing that, right? If you're on a mountain, you might want to know, like, how steep is it if I go that way? Not just, like, you're not on a mountain going, I have to go parallel to the latitude lines, you know? Like, I don't know, it's something from Tron, I don't know. Correct. So, for example, you know, they could start with a contour diagram like this, which is a 2D representation of a 3D surface. And the idea would be, if you're at this point A, if you're at this point right here, A, let me zoom in a little bit, if it'll actually zoom, but it's not, that's okay. And it's not drawing, so I'm going to restart. As long as I can figure out the change in Z or whatever the output is, so as long as I can find my delta Z, and I can find out my distance traveled, you can find your slope in that direction. So reading this contour diagram, we're going from 45 to 50. So we've gone up how much? How much have we gone up? 5. It's not a trick question. But then you'd also need the distance, right? So you need to know what that point is. That point looks like it's what, 125, right? So that's 125 comma what? I think it's what, 125. I got to lock this in. 200, is that the how high it is? Thank you. So this is 125 comma 200, and that point right here is what? That's 25 comma 225. 225. So could you find the distance between those 2 points? Like the actual, yeah, the distance formula, right? You're going in that direction. Like if you projected this line down, like what would the shadow be on the ZX plane? You'd want that distance. So it's going to be the square root of what? It's going to be the square root of 100 squared plus what? 125 squared. Doesn't matter about the sign because we're squaring, right? So that right there would be a small decimal, but that would be your rate of change in that direction. In that direction. Now, this is one straightforward situation. You're given a contour diagram, you can read it, and you can estimate it. So we're going to transition from that to using limits. So interested in finding what's the instantaneous rate of change at that point. And I remember when you first did limits, you made a table, and you anchor a point, and you go out a certain distance, then you go at another distance, and then you go at another distance, and you look as you would approach a limit. So all this is doing right here is instead of approaching from the left or the right, you're approaching from any direction you want. So the way they generalize it is they say you're going from some distance to the point, some point to the point AB, but you're approaching in a straight line. You're approaching in a directional vector. So the idea here is if you're approaching in a vector that has components u1 and u2, all you're doing is you're changing this h value, and as h goes to 0, these go to 0. So f of a plus this, comma b plus this, these go to 0, these go to 0, so you're getting infinitely close to f of AB. So what does this whole thing represent? This is the difference quotient. That's all it is. This is just the difference quotient written out so that you can approach from any direction. Now what we're going to do is we're going to put some specific limitations on this so we can keep the notation as clean as possible, because can the notation get stupidly... Yeah, you're not going to have to write that out every time you want to find a directional derivative. Yes. So it says if u is defined as u1i plus u2j is a unit vector, and I'm gonna underline something that's super important here. A what? Unit vector. We define the directional derivative fu. Nice, huh? Get to say fu a lot in this class. By this, the rate of change in the direction of u at AB is this difference quotient right here. This difference quotient right here. Now this right here is pretty, I think, directly, looks exactly like the difference quotient, right? The question I want us to answer is, why does it have to be a unit vector? And I don't want an answer right now. That's what I'm gonna lead you through right now, why it needs to be a unit vector. The answer is it doesn't, but it makes writing this out a lot easier if it is. If it isn't a unit vector, you're just going to either turn it into a unit vector at the beginning or take care of it at the end. The common practice is going to be to turn it into a unit vector at the beginning. The punchline, which you should know already, is we're working with unit vectors because we have to take magnitudes all the time. And when you're dealing with the number 1, life is simpler than when you have to deal with like the square root of 17. Although sometimes you will have to forcibly use the square root of 17. So where does this come from? They're both positive. Does one look like it's going to be more positive than the other? Maybe, right? But it's really hard to tell, right? Because here's the thing. The steepest it could be is is that, right? The shortest distance between the contour lines is going to represent the direction of the steepest incline, right? So you don't really know. You need to know more here. Someone stuck out there? Okay. Make it a unit vector, okay? Just do it at the beginning, please. So what is the u vector here going to be? It's going to be 1 over the square root of 2I, right? Plus what? 1 over the square root of 2j. So then you get to write f of u in the u direction at 1, 0 is going to be the limit as h goes to 0. And yes, that is how I write limit. Deal. F of 1 plus what?
1 over square root 2.
H, so h over root 2, right? And then 0 plus what? H over root 2 minus f of 1, 0 all over what? H. So you have this function. What is the function in this case?
X squared plus y squared.
Y what?
Oh, you can. So this is 1 plus.
Ah, there it is. Okay, let me get this back. There we are. The epiphany moment. Okay, so when you plug those in, you have to square both of them, right?
Yeah.
So when you do it out, I'm just going to shoot the algebra down, okay, because I just really don't want to do it at the moment. You end up with the square root of 2 times h plus h squared over h, right? So now this is the moment you feel better, because what can you get rid of? Yay, it's gone, right? So you end up with a limit as h goes to 0 of the square root of 2 plus h, which is what? Square root of 2. There's a way to do these faster, okay? I'm not going to sit there and make you do tons and tons of limits so you really appreciate the rules, but I want to unpack what this is a super dense part here, not just visually, but in terms of what they do. So what they start with is this right here. We just used this right here. We just used that, correct? The numerator of that fraction is delta f, the change in the function value. So if you wanted to say what this was, you could just say this. F in the derivative in the u direction is the limit as h goes to 0 of this thing, if you wanted to summarize it. Are we okay so far? All they're doing right now is saying that is delta f. It's the change in the output over h as it goes to 0. We okay with that? Then what it does is it just says out loud where delta f is this thing. Great. We already believe that's true. We write delta x. So if we were going to write delta x in this specific instance, x is you're going from AB, right? But you're moving a certain distance on the x value, right? And that's going to be h times what? u1, right? So the delta x in this case, and I'll erase this so you can see it, the delta x in this case is this difference, right? The delta x the a's go away, so you're left with delta x is what? hu1. So what is delta y? hu2, which should make sense because that is the definition. It's the change in x and the change in y. Are you with me so far? So we know, just as a side note, we already know from yesterday, remember the differential, everybody? Differential was delta f. We defined the differential, and we can go back to that 3D picture of like the tangent plane. The differential was, remember we used this yesterday? Remember that differential? Okay, but what do we now, in this case, in the case we're working with right now, what is delta x? H is right there. And what is delta y? hu2, right? So here's the thing. We had this statement right here. But we knew that the instantaneous rate of change was delta f over h, right? We now have a way of writing delta f, which is this thing, right? What's going to cancel? We now can write, it's an approximation, right? But what cancels? The h. So we now know that the directional derivative is approximated by this. But as h goes to 0, it is the derivative. It is the derivative at that point, the rate of change at that point. So what does this mean? You get this wonderful formula which states the derivative in the u direction is what? It's fx at AB times u1 plus fy AB at width times u2, where u1, u2 are what? The components of the unit vector. So you find the unit vector, you compute the directional derivative in terms of x, in terms of y, and then you're done.
So then you